Uh, okay, so I will just dive right into the next part. Minimize everybody here. Okay. So in the second part of our tutorial on using EDBO for Bayesian reaction optimization, we're going to look at a recent example that myself and Jason Stevens of BMS worked on, and that is optimizing a Mitsunobu reaction. So the general transformation shown in this poorly rendered chemical reaction scheme, so I should probably fix that before we post this. So the general transformation that we're interested in here today is basically the substitution of this benzylic alcohol with this indole. In the reaction that we're using to accomplish this transformation is called a Mitsunobu reaction. And based on Jay's sort of experience running these types of reactions at BMS, we identified 7 parameters which we are going to use to define our reaction space. And these 7 parameters include the azadircarboxylate, activating agent, phosphine, solvent as categorical parameters, and then substrate concentration, the azadircarboxylate equivalence, phosphine equivalence, and temperature as continuous parameters. So we imagine that these 7 parameters should sort of prove to be fruitful areas of search in this optimization. So that's basically what I mean by defining the reaction space, and this is entirely up to us as chemists. With those different components defined, basically we come up with a list of the different chemicals that we're thinking about including, and then our next task is to come up with the reaction encoding. In this particular example, I wanted to use the best reaction encoding that we found from our studies that we are sort of about to publish. And that means that we're going to use a customized DFT or density functional theory computed encoding. That being said, EDBO is designed to automatically encode in the case that you don't want to carry out those additional calculations. And you can use things like cheminformatics fingerprints or one-hot encoding, and things tend to work pretty well in that context as well. Okay, so we're going to use DFT encoding for the chemical components, and then we're just going to represent the continuous components as if they're sort of numerical vectors. Okay, so the first thing that I'm doing here is I'm loading the different chemical components here into a pandas data frame. And once I've loaded it and kind of trimmed away some descriptors that have keywords in them that we want to ignore, this is what we get. So basically, we just have CSV files where I've stored the descriptors for each of these components, sort of indexed by their SMILE strings, which is a 2D graph representation of the molecules. And you can see that for each one of these, we have chemical descriptors ranging from all sorts of different stuff, including steric and electronic parameters. Same for the phosphines, and also same for the solvents. So now that we have our encoding, we can move on to the next step. Again, as I mentioned before, we don't necessarily have to define these custom encodings. We can just pass to the optimizer different keywords such as one-hot encoding or Mordred, and that gives a Mordred chemical fingerprint in the case that you don't want to run all the calculations yourself. But it has the option of sort of specifying an arbitrary encoding in the way that I'm showing you today. So the next step in defining the reaction space is basically defining 3 dictionaries which kind of capture all of this information. This first one, which is the components dictionary, basically we specify each one of the different parameters. And for continuous parameters, we're going to specify our own grid. And this is because in the way that we're using EDBO today, we are going to explicitly argmax the acquisition function over a discretized domain. So we sort of choose our own grid of continuous parameters, which I think is pretty reasonable. And then the next thing that we do for those that are going to be sort of automatically encoded, we pass an encoding dictionary to the optimizer, and that's going to basically say for each of these concentration, equivalence, and temperature, that we're just going to encode those as their numeric values. And we have to do this in this context because EDBO is set up to automatically one-hot encode things if we don't specify the type of encoding. And finally, now we want to read in these external descriptor matrices as pandas data frames. And here you can see that for each one of our chemical components. So an important thing here when you're actually doing this is that we need to make sure that our keys in these dictionaries line up across the different across these different components, because that's how the optimizer is going to know how to sort of build the space that it's searching. Okay, so the next step is instantiating a EDBO Bayesian reaction optimizer instance, and then using it to actually choose which experiments to run on the left. So the class that we're going to use to do that today is called the BO Express class. And this is a somewhat more user-friendly sort of superclass of the main BO class, which is designed to sort of take some of the legwork out of actually sort of preparing and pre-processing descriptors and that sort of thing. So here, what we're doing is we're passing these 3 dictionaries to BO Express. We're choosing the acquisition function we want to use. Here, we're using expected improvement, as sort of shown in part 1. We're going to choose our initial experiments at random, and we want to choose 10 experiments at a time, so our batch size is 10, and we give our target a name, so it's not required, so we're optimizing. And just to stay consistent with the paper, while the BO Express class attempts to choose priors optimized for the type of encoding that you've selected, we want to use the priors that we sort of disclosed in our recent paper. So here I'm just going to reset the length scale prior, output scale prior, and noise prior. So this is a kind of unnecessary technical note in preparing the optimizer in the exact configuration that we used for the paper. Okay, so we basically instantiate this BO object, and it'll take a few seconds to run, and it's going to build a search space. And then once you're done, we can take a look at what the encoded search space ends up being. You can see that we've ended up losing quite a few descriptors in the encoded domain for the reaction. Basically, you can see some azide carboxylate descriptors. If you scroll to the end here, you can see each one of the different continuous parameters. You'll notice here that EDBO has automatically normalized and decorrelated the descriptor matrix for the overall search space. We can get access to the particular unencoded experiments using this get experiments option in the reaction module. So basically, we put everything that isn't relevant to the optimizer, so that's encoded domain and circuit model and acquisition function, in this sort of reaction container. So you can see the smile strings and the unnormalized continuous. We can also visualize components for a given reaction. So here's our first reaction in the space, where we've just printed that entry from the data frame, and you can see the 3 components: azide carboxylate, phosphine, and solvent here. Okay, so basically we've set up our optimizer, and we're ready to start choosing experiments to run in the lab. As I mentioned before, and specified with this initialization method argument in our instantiation, we are just using random sampling to choose our first 10 experiments, and that is accomplished with this init sample option. Here I'm setting a seed, so we get the same result if we run this again. And then once we do the sampling, we're going to use this export propose and send it to a CSV file called init. Basically, you can see it's been exported to the working directory here. And what we have is just the index entries here. So we have the smiles for the different components, the solvent, and then each continuous parameter. And basically what we're going to do is go into the lab. This is exactly what Jay did. Go into the lab, run these experiments, and fill in the yield column here with the results. So sort of human in the loop optimization. Okay, so and we can use this get experiments option to actually just look at the experiments selected in our Jupyter. It's worth noting that maybe you don't want to have to run this whole workflow if you shut your computer down or exit the window. So you can save this workspace just with a bo.save option. And this kind of pickles the whole thing for later. And then you can, if you open this document back up again, you can just load the optimizer in the same state that you were just working with. Okay, so now that we sort of have gone into the lab and run these experiments, we add the results with this add results method. And here I've stored them in the results folder, and you can see that they're in the exact same form as before, where we have now filled in the yield column. So get back to our notebook. Okay, so we've loaded the results, and then in order to fit the surrogate model, optimize it, and optimize the acquisition function, and then project forward in order to select a batch of 10. We can do all of that with a single command here. bo.run executes that method, and these are the encoded domain points that are automatically returned. Now let's say that once we run the optimizer, we want to run some sort of miscellaneous analysis, and we can plot the convergence. Here we've only run one round, so there's not really a convergence curve. But you can see that our best yielding experiment actually already gave us a pretty decent around 75% yield. Nice. We can analyze how well the underlying surrogate model fits the data on the normalized domain. You can see that here the Gaussian process model fits the data quite well. And then we can also write some more customized analysis functions. So here's an example of trying to visualize the batching algorithm and how it's sort of sampling the space in a one-dimensional projection. And so here's the acquisition function for the first two samples chosen out of 10 for the batch. You can see that it's sort of sampling in different places across the search space. And then once we're sort of satisfied with the analysis, we can export the next round of experiments, and just as before, go into the lab and fill those out. Okay, so that's kind of breaking down the workflow. But let's say you want to do this every time and you don't want to have to sort of execute all these lines of code. We can just write a quick workflow and drop it into a Python function, which does each one of these steps. And then all we have to do is go to the lab, run the experiments, load the results, run the workflow, and you can see the process repeating itself. So now we've gotten up on the second batch of experiments up to a healthy 90-ish% yield. The acquisition function has become a bit more complex, but you can see some areas have very low expectation value of improvement. Continuing forward, third round of experiments, we're up past 95% yield. And now you can see that the acquisition function is suggesting that the majority of the search space has 0 or near 0 expected value or expectation value of an improvement in yield. And so that indicates that it's unlikely that we're going to see improvements in this sort of region of the space based on the data that the optimizer has. And then we run one final round of experiments, and that basically gives us the quantitative yield. So within 4 batches of 5 experiments, we've basically achieved 99% yield in this reaction. And again, you can see that most of the space now has expected improvement that is close to 0, with exceptions of these 2 clumps. Okay, so I mean that's basically it. So we have iteratively gone back and forth, run experiments in the lab, read the data back into the optimizer, and sort of iteratively chosen the next experiments. So at the end, you can do whatever sort of analysis you want. If you just want the best yielding conditions, just go back into your results and find those. Here I've loaded all the conditions, and you can see, and then filtered by the top 5 yielding conditions. You can see that we actually had quite a few experiments in the end that gave us near quantitative yield. Maybe we want to get a breakdown of what the different process parameters were like across those top 5 yielding conditions. And you can see that that a couple different agents like carboxylates worked, a single phosphine worked, solvent didn't really matter that much, concentration, a couple parameters, and so forth. What is surprising here from the context of just the Mitsunova reaction is that actually you can see that 4 out of 5 of these top yielding conditions actually had the Mitsunova reaction running at elevated temperature, which is kind of unconventional. So you can see that the optimizer kind of naturally searched areas of chemical space that you might not anticipate as a synthetic chemist based on your understanding of the reaction. We can look further and just look at those components. You can see that the activating agents ended up being these amide bases in this particular system. And the phosphine, again, somewhat unconventionally, a methyl diphenylphosphine ended up being best. And again, as I said, solvent didn't really matter. So that about wraps up our sort of hands-on tutorial of how this all works. And I will note at the end that this analysis can really be run on any computer. So the laptop that I'm using today, I ran all of this analysis and it took about 8 minutes of compute time. So really, you should be able to use whatever computer you're working on to sort of run this sort of.
So the slow step is still the frickin' chemist.
Oh yeah, I mean that's the point of Bayesian optimization.
I know, I'm just making fun of the fact that the stupid chemists